Hey everybody, welcome back. I just wanted to put together a quick video here to explain how you should analyze the data from our last lab there in Module 2, where we collected all that BCA data, ran a page gel, and looked at the UV-Vis spectra of your purified proteins, because there's a lot to walk through there and a lot of chaos to sort out as well. So anyways, without any further ado, let's get started with that. First things first, though, I did want to share with you this slide here, just explaining how that BCA assay worked, because I realized today we didn't have slides for this, so you were just doing what I told you in lab, and that was about it. But anyways, the BCA assay is short for the bicinchonic acid assay. All right. So what's going to happen here is we're going to take your protein samples and denature them at high pH, around 11.5. So that working reagent that you added to them, that was an alkaline solution. Okay. It also contained copper ions. You remember it had that distinct blue-green color to it. The reason we added the copper ions is because they are initially in the copper 2+ form, but then they're going to interact here with the protein backbone, and that's going to change them to the copper 1+ form. Okay? So it's going to reduce them. So that's the reaction with the protein. But then, we're not done yet. There's another component to this reaction. There's BCA, so the bicinchonic acid. And what that will do is it will chelate those copper +1 ions and then form this complex that absorbs strongly at 562. So that's that purple color that you saw. It was the reduced copper ions in complex with the BCA. That's what gives you the purple color. That's what you measured in the lab. Is that absorbance there at 562? And the idea is that the more protein you have, the more copper +1 ions you generate, and then bind to the BCA to give you that purple color. More purple color equals more protein. Okay? So that's the raw data that you collected. But that's only the first step here. The next step is to take, let's see, where was the data that we had? Okay, for example here. The next step is to take this data, those absorbances, and figure out what they actually mean. So how do we correlate these absorbances with actual protein concentrations? Well, the way we do that is by running a standard curve. Okay, so remember, either I ran the standard curve or you guys ran the standard curve, depending on which section you were in. But we got data that looks something like this. There were a few different standard curves. I'm just picking one of them here as an example. For your lab report, I'd like you to go to this final data tab and use the standard curve data that's shown here. I do have the data for the Thursday lab as well here, but really that's just for your reference, for your curiosity. I'd like you to use this data over here from Wednesday because it was a lot cleaner. Okay, but anyways, no matter which data you use, what you want to do here is you want to take those points and plot them. And you can see here the data from Wednesday were nice and linear. That's exactly what we want to see. And then what we can do is we can take these points and get a standard curve equation. But we have to be careful about which points we include in that standard curve, because there might be some points like this one right here where the protein concentration was so high that the absorbance was above 1. I cannot trust that data point because the actual absorbance here is probably much higher than that 1.1. So I can't trust anything above 1. At the same time, I can't trust anything below 0.1. So these two data points down here, I'm also going to eliminate from consideration, leaving me with just these 5 data points here. Okay? So anything above 1, get rid of it. Anything below 0.1, get rid of that as well. Okay, so if I do that, here we go. This is what my plot becomes. And you see, you might have noticed that the standard curve equation changes slightly as well. Okay, that's because I'm only considering these 5 points instead of all 8. And I just want to show you real quick. So these data look great. We've got the equation up here. And we did that by right-clicking on this and then adding a trend line. Okay, but the other way you can do that in Excel is you can type in this equation, equals slope, then highlight your y values and your x values with that equation right there. And notice it gives you the same number, 1924.6, 1924.6. That's your slope, or your m in y equals mx plus b. You can do the same thing with the intercept here. Type in equals intercept, highlight your y values, comma, highlight your x values, close those parentheses, and there you get the negative 199 as well. Okay, so that's just nice because now we've got these numbers. We didn't have to retype them or transpose them from this equation up here down to here. Okay, so now we have this standard curve that describes how we can convert an absorbance value into a protein concentration. All right, so now let's do that with the values that we measured in lab. Okay, now what I've done here is I went through all of the data from Wednesday and Thursday, and honestly, I kind of cherry-picked what made sense and left behind what didn't. There were a few samples that were way too high in concentration. It really didn't make sense how high those yields were, or how high those protein concentrations were. Some were prohibitively low. At any rate, these values right here are pretty representative of what we found in lab. So it's these values, these absorbances, that I'd like you to use. Okay, don't go over to the Wednesday tab and look for your specific absorbance to use for TS Purple instead of the other one. Okay, to simplify my grading, I'd love it if everybody used the same numbers right here. Okay, so anyways, we have these raw A562 variables that are values. This is what you measured with the plate reader after that BCA assay was done. And in some cases, we had a dilution factor. So we have a cell for that here. None of these absorbances were diluted. But at any rate, I just want to walk you through this process. You always want to adjust your A562 by multiplying by that dilution factor. So just in case you had diluted it by 5-fold, you would multiply that original A562 by 5. But here, it's nothing exciting. They were all dilution factors of 1. Okay? So now we have our adjusted A562, and we can use our standard curve equation to convert those absorbances into protein concentrations. So according to the equation up here, my concentration is going to be equal to this 1924.6 times x, which is my absorbance. So that's y equals mx plus b. My intercept is negative 199.9. So I type that in there, and there you go. What this is telling you is that for the native AE blue sample that we purified with AEX, that had an absorbance of 0.589, which correlates to a total protein concentration of 933.7 micrograms per milliliter. And I can trust that result because that absorbance falls right in the middle of my standard curve. Okay? So I can be pretty confident in what that's telling me. So, BCA gives you that result right there. I'm only going to show it to you for AE blue, but you can imagine you could just take that equation and drag it down. But that result is the total protein concentration. I don't really want that. I don't need that. I need the concentration of my chromoprotein or whatever protein I'm trying to manufacture. So while that's the total protein concentration, Now I'm going to go over to our UV-Vis section here, and I'm going to use this absorbance spectrum to estimate the specific concentration of my specific chromoprotein. Okay? The way I do that is I look at this spectrum, and every protein, every chromoprotein has an absorbance maxima, this A max value here. So that's the wavelength at which the absorbance is maximized. For AE blue, for example, that occurs at 597 nanometers. For the other proteins, we have different absorbance maxima, but the general trend still applies. Okay? Now, I do want to point out here, the numbers that you see highlighted are slightly different than what are in the lab manual. That's a little bit of an oopsie on my part. What's happening there is I gave you the absorbance maxima for the native proteins, but you can see here 3 of these rows are for his-tagged proteins, and it looks like the his tag actually changes the conformation of the protein just slightly, but just enough to where it modifies the A max value. Okay, so instead of, I think it was TS purple, in the lab manual says something like 568 or something like that, it actually occurred at 578 here, or something to that effect. Okay, so that's a very good example of how these tags can change the activity of our proteins in very subtle ways by modifying their conformations. But anyways, I just want to mention that, just in case you were confused why the numbers might be a little bit different on this sheet compared to what you see in the lab manual. That's why. I gave you the values for the native proteins. Here's the values. We're going to use the same type of approach, but for the tagged proteins. Okay? All right, so anyways, with native AE blue, we don't have to worry about that. The absorbance maxima is 597 nanometers. So here we go. This is the absorbance spectrum that we collected for that sample. And if we scroll down here, here we go, 597 should occur right here between 596 and 598. And you see that's exactly what we observe, right? These two values, 599, are higher than the surrounding values. So that tells you that that point right there does occur at 597 nanometers. There we go. And the value, the absorbance at that point, is 0.599. So I want to put into this cell here 0.599. That is the absorbance at my absorbance maxima. If I'm talking about His EK4 red, all right, I can go over here to the His EK spectra. Here's the E4 red column. And what was it supposed to be? 580. Okay, so I scroll down, find 580, and there is my absorbance maxima for the His-tagged E4 red. So see that value is 0.178 and everything's lower on either side of it. So I want to put in here 0.178. Actually, was that the number? Yeah, it was. Okay. And you can repeat that process for each of the other proteins because we've got the absorbance spectra in these tabs here. Oh, they're somewhere. There they are. Okay. So we've got the absorbance here. Then we can convert that absorbance to a concentration of that chromoprotein using the Beer-Lambert law, A equals ECl. We just have to know two things. We have to know what E is, that's the extinction coefficient, and that's what's listed in this column here, and the path length L. Now, the path length L is actually easier to get. That's just the height of the water column in that 96-well plate. And if we add 200 microliters to a 96-well plate, we know the height is 0.19 centimeters. So you can see I already have that filled in for you here. And the extinction coefficients are right here. Okay? So if A equals ECl, we can solve for C, the concentration of our target protein, as A over EL. Now we know A E, and L. So I can just say the concentration of chromoprotein here, C, is equal to A, that cell, over E and L. So there you go. That's telling you that we have, what is that, 2 times 10 to the negative 6 molar, which would be 2 micromolar of our chromoprotein. But that doesn't really compare all that easily with what we got from the BCA assay, right? Because the units over here are microgram per mil. So to compare these two concentrations, I'm going to have to convert this from a molarity to a mass concentration. So to do that, we have this equation right here. The concentration in mass would be equal to the molar concentration times the molecular weight. That's going to cancel out the moles. And then we have grams per liter, but we want micrograms per mil, so we have to cancel out the grams, 10 to the 6 micrograms over grams, and the liters, liter over 10 to the 3rd mils. So we do that conversion, it ends up being this concentration times the molecular weight, and then times 10 to the 6th over 10 to the 3rd, which is just 1,000. And there you have it right there. So this is the concentration of the AE Blue in micrograms per mil. Now, you might be disappointed by this result, and rightfully so. You can see here, UV-Vis is telling us that we have a much lower concentration of chromoprotein than total protein. So we can use this as an initial estimate of purity, right? I could take the concentration of my chromoprotein, divide that by the total concentration of protein, and there you have it. The purity of our sample is only 8.2%. 92% of that sample is other E. coli host cell proteins. Okay? So that's a start, but certainly I would need to purify that further if I wanted to put this thing on the market, or certainly if I wanted to inject it into a human being. All right? So there is your proof that AEX, while we can use it to partially purify the protein, it's not going to give us 100% purity. Okay? Another thing I can do here with this number is I can calculate a yield. To calculate the yield, that's pretty simple. It's just the concentration of protein times the volume of the sample. And I have recorded here the volumes of all of our purified samples in this column. So what I can do is I can just say, okay, here's my chromoprotein concentration times the sample volume. I got 91.6 micrograms of AE Blue out of that purification. And again, that might be a little underwhelming, but it's higher than 0, right? But at any rate, what I'd like you to do in your lab reports is compare these purity and yield values across the different purification methods to see which method gives you the highest purity, which method gives you the highest yield. Okay? And you'll find that different methods have different advantages. All right? So yeah, just for the sake of argument here, let's go through and do all those calculations. Oh, what am I doing wrong here? I forgot about those cells. So that DN11 and F11, when I drag those down, I want them to be constant, so I put those $signs there. There we go. So here's our total protein values from the BCA. Now what's interesting here is that the AEX and the IMAC purified samples are in the hundreds of micrograms per mil, but our chitin purified samples are only in the dozens, right? So we have less protein here, but that's probably because we got rid of all the other impurities. Okay? Now let's move on here. Just looking at this his-tagged E4 red. Drag this down as well. Let's see, there's no problem with that, is there? Nope. Drag this equation down. So that's interesting. For the his-tagged E4 red, I get a much higher concentration of chromoprotein, and then I calculate my purity as this concentration divided by that one. And I say, ooh, look at that. The IMAC actually did a better job of purifying the protein than the AEX, but this is exactly what we expected, right? because that his tag gives the protein a lot of affinity for the IMAC that allows us to wash away most of the other proteins, or a lot of the other proteins, and then finally elute our his tag sample at the end. So good. Our IMAC did some good there. Now let's calculate yield. And we see another big change too, right? So the yield has gone up here compared to AEX. So the big difference here is that while the concentration of chromoprotein is only a few fold higher, we were able to obtain a much higher volume of this sample. So never forget that. The yield is the mass. It's not the concentration. It's the mass, or it's the concentration times the volume to give us a mass. Okay? So here, wow, that his tag, we got a much higher level of protein expression, a much higher level of yield. Okay? Now, there could be a lot of contributing factors there. Remember our AE blue, we sonicated that, and a lot of that protein just flowed through the column. It was damaged by sonication. So that 91.6 could probably be a lot higher. But nonetheless, that's what the data is telling you, right? That the his tag protein, you had a higher yield than the native one, okay? And you can repeat that for the rest of these samples, but I did want to show you just one example of a chitin sample. So let's go with AS Pink here. We've got our BCA data already. Now let's find the absorbance at that maxima, A562. Let's see here, that's in this tab. And there's AS Pink. And there we go. So A562 is pretty close. The absorbance maximum, it's kind of hard to tell here because I only took measurements every 5 nanometers. I was in kind of a hurry. Sorry about that. But let's just call it 0.092. Okay? So we're going to call that the absorbance at our maxima, 0.092. There we go. Copy this calculation down there. Same thing here. Okay. So a lower concentration of chromoprotein, right? But our total protein concentration was lower as well. So let's copy that equation for purity down here and look at that. So AEX gave us 10%, IMAC gave us 30%, chitin affinity is giving us over 100%. That's exactly what we expected, right? Because that chitin binding domain should be the only thing that binds to chitin. So we should have washed away all of our impurities, and that's exactly what we see here. Now, you might be a little bit concerned about that number because it's greater than 100. I want to point out that when we collected the spectra for these chitin purified samples, these values were quite low. They were pretty dilute solutions. So specifically, that AS Pink value that we just used was lower than 0.1. And I've told you before, we can't necessarily trust anything outside the range of 0.1 and 1. So that's probably what you're looking at here, is that this measurement is inaccurate. If that protein was more concentrated, we get a more reliable value, okay? So yeah, I would hope that it was 100%. Here I see that it's over 100%, probably because this is not accurate, okay? But that's great. I mean, greater than 100% purity, we know we don't have impurities at least. But then here comes the bummer. So for yield, I take that concentration times the volume, and we only got about 26.1 micrograms. So what is that? That's about 40 times lower than what we got from the IMAX system. So that's the trade-off that you're going to see in these samples, is that IMAC gave you a ton of protein, of his-tagged protein, but it wasn't as pure as the small amounts of chitin purified protein. So that's your trade-off, okay? There is no perfect solution to this problem. If there was, that's all I would be teaching. No, that's the reason why you're doing 3 purification methods in this module, so you can compare the pros and cons of each one, and that's the essence of your lab report, okay? Now, I do want to mention real quick, you might see another confusing result. I think when you run the numbers, the purity of the GFP sample is about 78%. Again, that was a very low absorbance. It was only 0.12, so there might be some inaccuracies there. Because the page gels certainly showed that the GFP was pure, right? If we go, where is it? I don't know if this is GFP, but AS Pink and GFP look the same. They had a single band with no other bands, as opposed to the IMAC and AEX samples. Again, this is probably just an inaccuracy from a dilute protein. Okay, so you're looking at about a 20% error of margin because those proteins weren't concentrated enough to make a good reading. Okay, but you'll still see that the yield is in the tens of micrograms. Okay. So the trends will all hold here. You'll see the highest purity with the chitin purified samples, but also the lowest yields. All right, but it's better to have a low yield of 100% purity than a high yield of something that still has something that could be toxic to a human being, right? So there you go. If I was to pursue this further, maybe I would use enterokinase on these samples, just like we talked about on the exam, to get 100% purity there and the higher yield. It's just it would be more expensive because I'd have to pay for the enterokinase. If I wanted to pursue the native AE blue, I'd have to follow that up with the size exclusion or HIC, hydrophobic interaction chromatography, to bump up that purity higher and higher. Okay? So that's the gist of that. Yeah, so after you do all these calculations, you should be able to obtain all these values over here and fill out the table that is required for lab report 2. Oh, one more thing. I made another oopsie in the lab manual. I gave you the extinction coefficient and absorbance maximum for GFP. This is the GFP from the jellyfish, Aquaria victoria. But we had Emile GFP in the his-tagged samples. So just use these values here for the his-tagged Emile GFP instead of what you see in the lab manual. Also, when I saw these spectra here that we thought was Emile GFP, that maximum is occurring here at about 488 nanometers. That is the Aquaria victoria GFP. Emile GFP, the maxima is pretty far right shifted. It's over at 503 nanometers. I think what must have happened there is I know that I have a chitin binding domain tagged GFP, and I probably just transformed, I got the wrong tube out of the box and transformed that into the E. coli instead of the Emile GFP. So sorry, Derek, Luke, Anna, and Emily, but it was an imposter that you were expressing and purifying all along in those cultures. But nonetheless, even though it just has that slightly left-shifted absorbance maxima, it's still a green fluorescent protein. It's just that when you look at those samples, that's a different absorbance maxima and a different extinction coefficient, okay? So this value only used down here, but when we're talking about Emile GFP, use this value up here. I've already got all that translated into the cells below. I just wanted to give you guys full disclosure on what I saw there. Okay, so I think that's everything that I wanted to discuss. If you have any questions on anything else about the lab report, please let me know. I might be slow to respond to email, but I'll try my best. Oh, there is one more other thing I just wanted to say real quick. Here we go, page shells. You're going to have to show page shells in the report, and I've shared these with you. There's not much more labeling to be done, but please make sure that you do have your target proteins labeled somehow, okay? And maybe fill out the rest of this ladder as well, okay? Oh, and then yeah, I wanted to talk through these results as well. So here are the gels from the chitin purification. And what you see in each case is that the lysate is loaded up with protein, so is the flow-through, just as we would expect. In some cases, the wash lanes either have a lot of protein as well, or they're pretty blank. That just depends on when you took your sample during the wash. If you took it early on, you probably still had some proteins that were eluting. If you took it later, then they were probably already gone. Okay, so don't worry too much if you see nothing in that wash sample or that wash lane. That's what's supposed to happen. All right. So anyways, we had some groups where you saw protein that came off the column, some where it was still trapped on the column. That is reflected here in these bands as well. So if we look at TS purple, that's where we had some protein come off, but some was still stuck on the column. We definitely see a band here for the chromoprotein and the elution fraction. And we only see a single band there, right? So that's important. That's because that is 100% pure. Okay. But then if we look at this band where we have the sodium hydroxide wash, where we forced everything off of those off those beads, we do see some uncleaved chromoprotein up here. So whenever the chromoprotein has the chitin binding domain tag and the intine, it's going to be a higher molecular weight, so it's going to appear larger on the gel. And you can see, here's the fusion protein in the lysate, right? It's that nice dark band. We do see some in the flow through, probably because we saturated these beads. We added so much that some of that protein flowed through. And then we see a little bit of it left on the sodium hydroxide wash here, but that sodium hydroxide looks like it might have actually increased intine cleavage somehow because we see a lot of chromoprotein come off in this fraction as well. Maybe that too was also just chromoprotein that the intine cleaved, but then for some reason the chromoprotein stuck to the beads, or it denatured, it aggregated there. Either way, we would see it here on this gel. Okay. Now, what was really confusing about TS purple, though, was we took this sample, the elution sample, and we put it onto a 10 kDa spin filter, and all that color came through. And at the time, I was worried that, uh-oh, that protein must be damaged, and maybe we're just looking at the chromophore. But look at this. The page gel tells us that whatever went through that 10 kDa filter was actually still protein, and it was the same molecular weight as what we expected to see. So this suggests to me that the filter that I just happened to give, Nick and Nicola, was broken. It must have had a hole in it, so it let all of that precious TS purple through instead of filtering it. That's what the page gel is suggesting. If that protein had denatured, I would have expected to either see nothing here or seen something at a much lower molecular weight. So yeah, we got a pretty good run for TS purple there. It's just not included in the Excel sheet because the absorbance readings we got were really, really low. So it worked, just tragically the filter didn't work. That was the weakest link in the chain. For Emil GFP, we didn't see any color on the beads because it's a fluorescent protein, but what I want to show you here is this is just a perfect example of what a chromoprotein chitin purification should look like. We have the fusion protein over here present in the lysate. A little bit of it flowed off in the flow through, but then after cleavage, we see a single band. It's faint, but it's there. We see it here in the elution. That's exactly what you want to see. And same thing for AS pink. We see the fusion protein here, but then after we cleave it at low pH, all we see is this protein over here. Okay. AE blue, we started with nothing, we ended with nothing. E4 red, we started with the fusion protein, and it looks like it just never cleaved, even in that sodium hydroxide wash. So E4 red, we'd have to go back to the drawing board there. Maybe this tag's not going to work at all. Maybe we could mutate a few residues right where the intine and the chromoprotein are joined together, and that could make it work better. It would take a lot of trial and error. But TS purple, Emil GFP, and AS pink, this all worked. It just worked at a low efficiency. So you'd have to do some more troubleshooting to really optimize protein production there. Okay, so that's all the page gels. Please do let me know if you have any questions on those. Otherwise, happy report writing. I'll see you guys around.